everyone. Today I am going to explain the topics dual space, contravariant vectors and covariant vectors. First we will see what is dual space. To understand dual space, first we need to know what is vector space. So let's start. A non-empty set V of elements called vectors is said to be a vector space over field F if the following conditions are satisfied. First property is that V with composition addition should be an abelian group. To be an abelian group, a vector must satisfy these 5 properties. First is closure property, that is x plus y belongs to V for all x, y belongs to V. Associative law, x plus y plus z equal to x plus y plus z for all x, y, z belongs to V. Next is existence of identity, x plus 0 equal to x for all x belongs to V. Next is existence of inverse, x plus minus x equal to 0 for all x belongs to V. Next is commutative law, x plus y equal to y plus x for all x, y belongs to V. In general, these 5 properties are the conditions that a group must satisfy to be an abelian group. Next property is that each scalar in field F can be combined with each vector in V by scalar multiplication. For all x belong to F, x, y belongs to V. Next x alpha 1 plus alpha 2 equal to x alpha 1 plus x alpha 2 for all alpha 1 alpha 2 belongs to F and x belongs to V. Next x plus y alpha equal to x alpha plus y alpha for all alpha belongs to F, x and y belongs to V. Next is 1 into x equal to x for all x belongs to V. Now, before moving on to dual space, we need to know one more thing, that is linear functional. A vector space V over a field F is called a linear functional if Fa plus B equal to Fa plus Fb, Fk into A equal to K into Fa, where A, B belongs to V, K belongs to field F. Now the dual space is the set of all linear functions that satisfy these conditions and is denoted by V star. Now we move on to the definition of dual space. The set V star of all such linear function over a field F is a dual space under the operation of vector addition and scalar multiplication as defined by U plus V A equal to UA plus VA for all UV belongs to V star and for all A belongs to V, and alpha UA equal to alpha UA for all alpha belongs to F and for all A belongs to V respectively. Thus V star is the dual space of vector space V. Now we move ahead towards contravariant and covariant vectors. To understand this topic, we must know first what is n-dimensional space. In 3-dimensional space, that is 3D space, a point is determined by a set of 3 numbers called the coordinates of that point, that is x, y, z. Okay? If a point is represented by a set of n real numbers, that is x1, x2 up to xn, or we can write as x superscript 1, x superscript 2 up to x superscript n, where the numbers 1, 2, 3 up to n are suffixes, then all the points corresponding to all values of coordinates are said to form an n-dimensional space, that is denoted by Vn. Thus, a curve in n-dimensional space Vn is defined as collection of points satisfying the equation x superscript I equal to x superscript I u, where I is from 1 2, 3 up to n, and u is parameter, and x superscript I, u are the n functions of u. Next, superscript and subscript. If a tensor is written like a, j, I, then the suffixes j and I are called superscript and subscript respectively. The one written above is called superscript and the one written below is called subscript. Move on to contravariant and covariant vectors. Let ai, where a is 1, 2, 3 up to n, be n functions of coordinates x1, x2 up to xn. If the quantities ai are transformed to any other coordinate system written by this, then according to rule this, ai equal to a alpha del xi upon del x alpha, then the functions ai are called components of contravariant vector. Let ai I equal to 1, 2, 3 up to n be n functions of coordinates x1, x2 up to xn. If the quantities ai are transformed to another coordinate system x1, x2 up to xn according to the rule this, ai equal to a alpha del x alpha del xi, then the function ai are called components of covariant vectors. We can say that in contravariant vectors the suffix is written in superscript, and in covariant vector the suffix is written in the subscript. Here important point is that the covariant and contravariant vector is also known as covariant and contravariant tensor of rank 1. Similarly, let aij, ij in superscript, ij is from 1 to 3 up to n, be n square functions of coordinates x1, x2 up to xn, and let these transformation to xij in the other coordinate system x1, x2 up to xn according to the rule aij equal to a alpha beta del xi upon del x alpha into del xj upon del x beta, then aij are called components of a contravariant tensor of rank 2. We know that rank is defined as the total number of indices per component. So here 2 indices are there, so rank will be 2. In previous page, here 1 indices was there, here 1 indices was there, so the rank is 1. If aij written in subscript and ij is from 1, 2 up to n, be n square functions of coordinates x1, x2, xn, and if aij are transformed to aij in other coordinate systems xi, x2 up to xn by the rule aij equal to a alpha beta del x alpha del x I del x beta del x j, then aij is said to be covariant tensor of rank 2. As we can see, there are 2 indices here also, so here also rank will be 2. If the n square functions is written as a ij, where I is in superscript and j is in subscript, then ij is from 1, 2 up to n, or coordinate system xi be transformed to aij in another coordinate system xi according to the rule aij equal to a alpha beta del x bar I del x alpha del x beta del x bar j, Then Aij are said to be components of mixed tensor of rank 2. Here also 2 indices are there, so rank will be 2. So here we wind up with our topic. Thank you. If n square functions Aij I comma j equal to 1 to up to n or coordinates xi be transformed to aij in another coordinate system xi according to this rule, that is a ij equal to a alpha beta del xi del x alpha del x beta del xj, then aij are said to be in components of mixed tensor of rank 2. Here we notice that I is in superscript and j is in subscript. So also here there are 2 indices, so also the rank will be 2. So here we wind up with our topic. Thank you.